Hi, my name is Shahnawaz. In this lecture, we'll introduce Zariski topology on projective space. In last lecture, we introduced the sets of the form UI, which contain all the points of the projective space of the form A naught through AN. So they are the points in the projective space whose ith coordinate is non-zero. So using this notation, we can identify AN with the set U0. So we can identify these two sets. So a point here, say A naught, I mean A1 through AN. So we can identify this point with the point one A1 through AN. So this is the point here. So that means we have an inclusion AN, an inclusion from AN to the projective space PN, while this point A1 up to AN is mapped to the point 1 A1 up to AN. So this means that we can write Pn as the union of U0, which is AN, and everything else, which is what we denote by H infinity. So H infinity is all the pointers of Pn other than the pointers in U0. So where this H infinity, so it is this set of all the pointers in Pn other than the pointers in U0, which are the pointers of the form A0 to AN in Pn, whose zeroth coordinate, A0, is 0. So this H infinity is called the hyperplane at infinity. So one can also view this H infinity as the zero set of the polynomial x naught. So now we have examples of some zero sets, which are what we call in upcoming lectures the projective uh, sets. So we have the empty set, so it is actually the zero set of the constant polynomial, say 1, and the affine space itself, this is the zero set of the empty subset of the polynomial ring in n plus 1 variables. Now let us suppose this is example 1. Now we have example 2 here. So let us consider a homogeneous polynomial, say f in the polynomial ring k x naught up to xn. So this is a homogeneous polynomial. Say of degree 1. So it is of degree 1. So then the zero set of this polynomial, which is subset of the projective space, so this is called a hyperspace, a hyperplane. So this is called a hyperplane. So actually this is one word. So this is called a hyperplane. Now for example, if we look at H infinity, so H infinity is the zero set of the polynomial x0. So this is the hyperplane at infinity. Now we have one more example. Now there are the lines in the affine n space, I mean in an, which do not intersect. However, any two lines in Pn, they are going to intersect. So the lines, so if we look at the lines, say zero set of x1, which is, and zero set of x1 minus x0, which are subsets of P2. So if we restrict these two lines to affine space, and by I mean in the, if we restrict these two lines in A2, then we have this x naught equal to 1 there. So then we have these two lines, I mean x1 is equal to 0. So we have the lines x1 is equal to 0 and x1 minus 1 is equal to 0. So they are the parallel lines in the affine space. So in A2, so they are not going to intersect in A2. However, they are going to intersect in the projective space. So note that these x1 and x1 minus x0, they are in the polynomial ring k x0 x1 and x2. So they restrict to parallel lines in A2, and hence do not intersect. I mean the rest of parallel lines, the zero set of x1 and the zero set of x1 minus 1 in A2, and hence do not intersect. However, but in P2 they intersect. So if we look at the point of intersection, so we have x0 is equal to 0 and x1 minus x0 is equal to 0. So solving these two, we get x0 is equal to x1 is equal to 0. So that means they intersect at the point 0, 0, 1 in P2. Note that this coordinate over here, this cannot be equal to 0 because in P2 we have removed the origin. So instead of 1 we can have some non-zero element here, but then we can normalize that I mean that line to get 1 here. So this point is, of course, so this point is actually in h infinity, which is subset of P2. So the situation here is like this. So we have a line at infinity, let us call this h infinity, and we have these two lines. So this is the zero set of x1, this is the zero set of x1 minus x0. So they are going to intersect at this line. So this point over here, this is a point 0, 0, 1. So this point lies on the infinity. Now we have one more example here. So let us call this example 4. So if I take a point P, suppose this point P is called A0 up to AN. So this is a point in Pn. Then this point P as a set. So this is actually the zero set of the system of equations, system of polynomial equations a1 x naught minus a naught x1. Similarly, a2 x naught minus a naught x2, and so on up to a naught a n x naught minus a naught xn. So hence this is a zero set. Now we have some definitions here. So we have the first definition. So we say a polynomial. So a polynomial, say f in the ring k x naught up to xn. So this can be written as, so we can uh, write this f. This can be written in a unique way as a sum. So we can write this f as the f0 plus f1 plus so on plus f d. So as a sum of forms fi of degree I. So the fi is called the homogeneous. So the fi is called the homogeneous component of f. So for example, if we take a polynomial, say we have, so for example, we have a polynomial, say f in three variables, say x naught, x1 and x2, where this f of x1 x2 x0 x1 x2 is given as, suppose it is called uh, a naught x naught cube plus say a1 x naught x1 square plus a2 x1 x2 cube plus a3 x, say x naught square x2 square plus a4 say x say x2 to the power 5. So then we can write this as the, so we have homogeneous elements here. So this is of degree 3, this is of degree 3, this is of degree 4, 4 and 5. So we can write this as f3 plus f4 plus f5, where f3 is the homogeneous component of degree 3, so which is equal to a naught x naught cube plus a1 x naught x1 square. Similarly, we can write f to the power 4 as a2 x1 x2 cube, so this is of degree 4, and a3 x naught square x2 square, and finally f5 as a4 x2 to the power 5. So this is the decomposition of f into homogeneous components. So we have one more definition here. So we say an ideal, say I, the polynomial ring k in variables x naught up to xn. So we call this is a homogeneous ideal if uh, it is generated by the, sorry, if it is, so if for every, so if for every f in I, this is if and only if condition, if for every f in I, all the homogeneous components are in I. So they are in I. Now we have a small result here. Let us call this a proposition. So it says that an ideal I in the polynomial ring k x naught up to xn. So this is uh, homogeneous if and only if it is generated by homogeneous polynomials. So let us prove this. So first assume that I is homogeneous. So assume that this I is homogeneous. So if this is the case, so let us suppose, so let f alpha be generators of I. So now I being homogeneous, we can write for each alpha. So for each alpha, we can write, so we can write f alpha as, I mean, as a decomposition in the homogeneous components up to say f alpha of degree d. So this is trivial, we can do this. So but it is given that I is homogeneous, so each homogeneous component of F alpha is actually in the ideal. So but F alpha I is inside I for all I equal 0 up to D. So the reason is that I is a homogeneous ideal. So, so if this is the case, it implies therefore if I look at this collection F alpha I, so this is so this collection over here, this is a set of homogeneous polynomials which generate I. So this is a set of homogeneous polynomials which generate I. So let us do the converse. Now conversely, let us assume that I is generated by homogeneous polynomials Gi. So conversely, let I be generated by homogeneous polynomials. Say Gi. Then for any f we can, so then for any f in I we can write, so we can write f as the finite sum. Let us say I goes from 1 to m ai gi. So note that these gi's are homogeneous, but these ai's they need not be homogeneous. So where ai's they are the elements in the polynomial ring in n plus 1 variables, need not be homogeneous. But gi is homogeneous. Uh, Thus, the homogeneous part of ai gi degree g. So the homogeneous, uh, I mean, the homogeneous part of say ai gi of degree d. So this is actually the term ai to the power d minus degree of gi times gi. So one can note over here. So this term over here is of degree d. So thus it follows that so if I look at the degree d component of f, so we can write this as this finite sum ai to the power d minus degree of gi times g. So one can note that the sum over here, this is an element of I. So this implies that this I is homogeneous. So hence I is homogeneous. So now we have one more definition. So let us suppose that, so let I be a subset, I be an ideal in the polynomial ring in n plus 1 variables. So this is given to be a homogeneous ideal. So by home I mean homogeneous. So then the zero set of, so I just mentioned here the projective. So in the projective, zero set of I is the set Zi, and it is given by definition. So it is all the pointers P in the projective space such that f of P is 0 for all homogeneous f in I. Similarly, we have the definition for the ideal of a set, ideal of a projective set. So let X be a subset of Pn. So the homogeneous ideal of X is by definition the set of all, I mean it is actually the ideal, so it is better to draw these angles. So it is the set of all polynomials in the polynomial ring K in n plus 1 variables. Uh, so all homogeneous polynomials, I mean, they are homogeneous such that f of p is 0 for all p in x. So we have a remark here, that is, if f is not homogeneous, can we define the zero set of f? So it's a remark. So if f in the polynomial ring is not homogeneous, is not homogeneous, so we can define the zero set of f to be the set of all pointers a naught up to a n in the projective space such that f of a naught up to a n is 0. So this has to be true for all representatives of this point. So for all representatives of P. So since we can decompose F into homogeneous components, so one should note here, so since we can decompose F into homogeneous components, uh, I mean we can write F as the homogeneous component of degree 0 plus the homogeneous component of degree 1 up to the homogeneous component of degree d. Assume that f has degree d. So then we can write the zero set of f as the intersection of the zero status of the homogeneous components. So this I goes from 0 to D. So roughly speaking, if f is not homogeneous, z of f does not give us one but many equations. For example, if f has non-zero, so if f is, so one can note here. So if f has non-zero part, constant term, then one should note that the zero set of f is always empty. So it is the case when f is not homogeneous. So using this remark, we can drop the homogeneous conditions in the previous two definitions. I mean, we can drop the homogeneous term over here, and we can drop, I mean, we can also drop this condition of homogeneous here. So therefore, we have the following definitions of zero set is an ideal of a set. So this is the definition. So if f is in the polynomial ring, let us call this, let us take the ideal. So it is in the polynomial ring in n plus 1 variables. So this I is given to be, is a homogeneous ideal. Homogeneous ideal. Then we can define zero set of I to be the set of all the points in the projective space such that f of p is 0 for all I. So we have dropped the homogeneous condition here. Similarly, for the for the ideal of a set, we can also drop the homogeneous condition. I mean, if x is a subset of Pn, so this is a projective algebraic set. By projective algebraic set, we mean it is zero set of some set of polynomials. So algebraic set, then we can write I of x to be the set of all polynomials. So we have dropped here the homogeneous polynomials. We are saying just the set of polynomials in the polynomial ring such that f of this little p is 0 for all p in x. So if we change what we mean by the zero set by saying it should be the zero set for all representatives, then we can use same definitions as in affine case. So now finally we are going to introduce the Zariski topology on Pn. So we have a proposition here. So suppose this is the first item of the proposition. So let x and y be subsets of Pn such that uh, x is contained in y, then the ideal of x is contained in ideal of, I mean ideal of x contains the ideal of y. So the proof is same as I mean we are going to mention here certain items, and the proof of all the items will be same as in the affine case. So this means when these x and y's they are projective algebraic sets, So then this function I is actually decreasing function. Similarly, we have so if let S and T be subsets of the polynomial ring x1 up to xn, uh, such that such that S is contained in Y and T, then zero set of S contains zero set of T. In other words, this zero Z function is also decreasing. Then we have third item. It says that if uh, X is a subset of Pn, so this is a projective algebraic set, then the zero set of uh, I of x is actually x. That means this function 0 composed with I, it behaves actually as the identity function on Pn. So as we have seen in the affine case. So finally for the fourth item, so if J is an ideal in the polynomial ring, uh, such so this is a homogeneous ideal, then the ideal of zero set of the ideal J, it actually contains the ideal J. So this is also same as in the case of affine spaces. So then we have the fifth item. So using these, fifth item says that if S is just a subset of the polynomial ring, then the zero set of S is same as the zero set of the ideal generated by S. Now we come to the results which give us the Zariski topology on Pn. So these two items we are going to, I mean, we are going, this is the item sixth. Let us drop a star here. So for a family, say S alpha of set of forms in the polynomial ring, we have zero set of the union of um, all S alphas. So it is actually the intersection of zero sets of S alphas. And finally for the seventh item, we have, so for S and T to be subset of the polynomial ring, so let us suppose they have two sets. So B2, so let us suppose that, so let S and T be sets of forms then the zero set of the product st is actually the zero set of s union zero set of t. So these two items, so from these two items we see that the arbitrary intersections and finite unions of projective algebraic sets are projective algebraic sets. So this allows us to introduce a topology on Pn for which the closed subsets are projective algebraic sets. So we will not prove these items here because their proof is similar to the case in affine space. So we just leave them as assignment for the viewers. So this allows us, so the items sixth and seventh uh, allows us to introduce a topology on Pn for which the closed sets are projective algebraic sets. And this topology is called the Zariski topology. So simply if we declare these sets to be closed sets, then we have a topology, and that topology is called the Zariski topology on Pn. So let us write this in definition. So the Zariski topology on Pn is a topology uh, so it is a topology whose closed sets are projective algebraic sets. So now if X is any subset of Pn, so in the induced topology, I mean the subspace topology. So the induced topology, which is same as the subspace topology on X, is called the Zariski topology on X.